Bismillahirrahmanirrahim. Welcome students to the online lecture of Digital Logic Design. In the today's lecture, we will be discussing memory registers. In the last lecture, we discussed the design of sequential circuits using the JK and the T flip-flops. In the current lecture, we will be discussing the memory registers. Because in this week, we will be discussing two kinds of topics. One is the register and the second one are the counters. So first, we have a just brief introduction about both of them. A register is a basic or the smallest memory storage element. Generally, a flip-flop is used to store a 1 bit of memory. So if we have a combination of flip-flops, say we have a combination of n flip-flops that store n bit of data, then we can say that we are representing an n-bit register. An n-bit register is representing an n number of flip-flops. Each flip-flop is separately storing a single bit data. Generally, in the registers, we could have some additional combinational logic attached to the flip-flops input for certain data processing tasks. But the main purpose of the register is just to store the data and the manipulate information in any given digital system. While there is a special type of register which we call a counter, but we will be discussing it as a separate head. Counter is a register, but that goes through some predefined or predetermined sequence of binary state. It means if the register's output could only follow a certain pattern of the states, then we call it a counter. While a register could store any different values, a counter must have a predefined sequence of binary states that it should follow. Counters are generally employed in circuits related to the sequence and the control operation. First, we would be discussing a very simple kind of register, that how a basic memory storage element works. In this diagram, we are representing a 4-bit register. Each of the bit is represented or stored in a form of a D flip-flop. Here you can see that we are having 4 flip-flops here. Each are of type D. We have regular inputs that are attached to the flip-flops. First one is the D input, which we call the data input. Each has a separate input here. Because we are dealing with the 4-bit data here, so I0 to I3 is basically representing here the data bus, you can say, or the input to the system. Whenever we want to load a certain data, we just apply the 4-bit data on these lines, and on the next clock cycle this data will appear on the output values from A0 to A3. We are having also in synchronous reset here, which is represented here by the clear signal. Whenever this values goes to 0, all of the flip-flop that are connected to it would go into the reset state, making all the output values goes to 0. So in this way, what we do is that we simply apply the input to these 4 input lines from I0 to I3, and on the arrival of the positive edge of the clock, what happens is that the input is connected to the output, and A0 would get the value of I0, A1 would get the value of I1, A2 would get the value of I2, while A3 would get the value of I3. Generally, this kind of simple register is also sometimes available in a standard IC configuration form, which is also represented in a form of this block diagram. Now we would be discussing some other things that are related to these registers. Suppose we want to have a register in which we want to control that what kind of input system should have, or we can say that rather when that input should be applied to the system. Generally what happens is that these input lines I0 to I3 are connected to the main data bus of the system. So whenever a new set of values arrives here from I0 to I3, on the next clock edge these data inputs move towards the output. But suppose in our given system we require that only at certain times that we should have values from the external bus or the data bus, and we could also retain the values of the A0, A1 and A2, A3. This is probably not possible to retain the values of these three in the standard configuration that we have discussed in the last slide, because these pins are connected to the data bus. If we want to retain these values, then there are two things that could happen. First thing is that we somehow disconnect these lines from the main data bus, which is generally not possible. And the second thing is that if we may stop this clock signal somehow, so that it doesn't arrive, positive edge doesn't arrive at these flip flops, and we don't have a change in the output. So in this way we can retain these values. Generally, anything or combinational circuit that is attached to clock signal is not recommended because of these various speed and other issues that are related to the clock signal. So we should have a certain kind of extra circuitry involved in the system so that we can handle these kind of constraints. For solving this constraint, we design a 4-bit register with parallel load. In this register, what we do is we attach a mux with each of the input of the flip-flop. This each combination here is representing a mux signal, and from this mux signal, the selection line is this load signal. It has two inputs. One is the input from the main data bus, which is represented as I0, I1, I2 and I3, while the second input is connected from the main output of the same flip-flop. So by appropriately selecting the value of load, we could either select the or retain the value of the current state, or we could select the value from the external input. If we say that the value of load is equal to 1, if we assume that the value of load is equal to 1, then what happens is that when the value of load is equal to 1, then our system is basically connected to the external inputs I0, I1, I2 and I3. While if the value of the load is equal to 0, then what happens is that our system is connected to the outputs of their current flip-flops. Like this, if value of load is equal to 0, then we would have basically I1 would be connected, A0 would be connected here. So our system will retain its current output. Similarly, same is the case with A1, A2 and A3, because all of them are following the same structure, and we all of them are having a mux of this kind at their input. So, and each of the selection line are from the same load signal. So depending upon what value we would like to select, either we would like to have these four input from the data bus, or we would like to retain the values, we can select the value of load. So can we can get the parallel load value loaded to all these 4-bit of data. Now we would be discussing and another important type of register. This is known as the shift register. Generally, a register is called a shift register if it has the capability of shifting its bits from, say, to the one neighbor to another neighborhood cell. So if any register has a capability of shifting its binary information towards its left side or its right side, then we call it as a shift register. Its example is considered in form of this block diagram. We are representing here a 4-bit shift register. In a shift register, each of the flip-flop that are attached in the cascaded form have a same clock signal. So the whole system works in a form of a similar clock. While we apply input from only the one side, and the last of the cascaded flip-flops, we get the output signal. So if we apply, say, serial input from this side, then actually our data is moving in this direction. You can say from left to Right. So basically, whenever a clock signal arrives, whatever data was present here would move to here, towards here, and whatever the data was present here originally would move to the this output. Similarly, same with the all the flip flop. So in this way, a serial transmission occurs that we perform each operation bit by bit instead of the parallel combination or the parallel processing that we have seen in the last slides. If we apply say a signal value of 1 here and we assume that all the rest of the values were equal to originally equal to 0, then what would happen is that after the first clock cycle or the first positive edge of the clock, this signal will appear here, and similarly rest of them will have the value of 0. And after that, the one that appear here, when the next clock edge arrives, this signal will move to here, and after the next clock edge it would move to here, and after the fourth clock edge it would move towards the output. So in this way we design a serial shift register in which we have a data in the form of a serial in a bit by bit, and we are moving in this diagram, we are only moving from you can say left to right direction. So there is only one shift that is possible in this case, and that is the right shift. Now, if we want to make some changes in this serial transmission case, we could always add few other functionalities that are related to the serial processing case. The most important is them that how we could control this whole shifting operation of the system. Just like the parallel load operation, we had a load pin, and from that load pin we were able to control what kind of data should be at the input of the flip-flop. Similarly, in the serial processing, because now we are dealing with the one bit at a time, so we need a mechanism from which we can decide that how much data we want to shift. Say we want to shift the data 2 bits, so we want to shift the data 3 bits. So there should be some kind of control that should be available to the user, so that from that control we can control the serial data input output manipulation. For this purpose, what we do is that we add an extra signal along with the clock signal. We called it as a kind of a gated clock signal, in which we have a extra signal which is known as the shift control. Whenever both of them would have a value of 1, only then this shift could occur. Suppose this is a shift register here, and this is also a shift register here. Whenever a shift values have a pulse of 1 here, then what would happen is that on the positive edge of the clock, the input to this register would move to the output of this register, which is connected to the next input register. So in this case, when the next clock cycle arrives, this input would be equal to the output. So in this way, we want to design a mechanism. Basically, what we are doing here is we are connecting or communicating two separate devices, and we are transferring data from one device to another. Both of them are having certain shift register. This is shift register A representing the say device A, while this is shift register B representing the device B. Both are operated from the same clock signal. What we want to do is we want to transfer the data of shift register A towards shift register B. Simply, but what we do is that we have gated the clock here. Whenever the shift operation goes to the 1 and we have a positive edge here, only then this clock signal would affect this shift register, otherwise it will not affect. So in normal operating condition, we can just set it to 0 so that there is no shifting process again. There is another important thing that is present in this circuit. You can see that the output of the shift register is again fed back to the same register. This is done because we want to store the value of A. Because if we don't connect its output to the input, what would happen is that say A is a 3-bit system. It has a value of say 1, 0, 1. After the first clock cycle, the 1 would move to the shift register B. After the next clock cycle, 0 would move to shift register B. After the third clock cycle, 1 would move to here. And if we are not connecting it in a form of a feedback, there will be simply 0 inserted in all these rest of the register spaces. So we would not be storing the value of A. So in this way, if we connect it in the form of a feedback system, what would happen is that after the 3 clock cycle, the data that was present in the A is transferred to the data that is present in the shift register B, and at the same time the value of A is also retained. The output of this system is given by the output of shift register B. So whenever the value that is present here after next 3 clock cycle, it would be moving out in a form of a single bit at each time. We can also discuss it in a form of an example. Say we have a clock signal like this. Our system is operating here on, say, the positive clock cycle, and we are having a shift signal here. As we have seen that our clock signal was gated with the or and gated with the shift control signal. So whenever this value is equal to 1 and we have a positive edge of clock here, only then what would happen is that our data would be transmitted. So if we AND both these signal, we would get the clock signal like this one. So if we AND both these signals, we would get a clock signal like this. This clock signal would only have 4 pulses. So if we want to shift a data of 4 bit from shift register A to shift register B, then what would happen is that, say, initial value of the register A was 1011, while that of shift register B was 0010. After the first pulse, what would happen is that the first output value A would move towards the B here. Similarly, after the next clock cycle, what would happen? The value at the output of A here would move towards B. Similarly, the next value after the third clock cycle would move here, and after the fourth clock cycle, the last value would move towards B. Now you can see that the value of B here is now equal to A. And because of the feedback that we have used from the output of A towards the input of A, we are also able to retain the same value of A after the fourth pulse. So in this way, a shift operation occurs and we transfer our data from a shift register to an other shift register. Say if we could add extra functionality to the shift register that we have discussed so far, in a way that we have a, say, n bit shift register which comprises of, say, 3 different flip-flops, and we have accessibility of each output of each of the flip-flops that are involved in the system. Then we could also get the output in a form of a parallel form, because we are also getting the values, already getting the values in the form of a serial output, but we would also be getting the values in form of parallel too. So there could be an extra functionality that could be added to the system. And in a similar way, we could also add an extra circuitry to the system, like the one we added in the load registers case, that we are able to control the loading part of the inputs to the all the serial system, and say we could add separately values to each of the shift register that is involved in this system. Then this could be the other functionality that we could add to the system. Generally, if we have a register that could move the data both in the left direction and the right direction, we call it a bidirectional shift register. And if we have a register that is also capable of moving in both direction and also capable of providing us the parallel load capabilities, then we call it a universal shift register. So some of the registers have some properties, while some may have all these properties that we have defined. So in general, if we could add following kind of properties to the shift register. First is that we could have a clear pin that could be set to 0 to make all the outputs of the flip-flops that are involved in the system goes to 0, or make them to the reset state. And then we have a clock input to synchronize the operation. This is generally present in most of the shift registers and the parallel registers. Then we have a shift right operation and the shift left operation. So we have both the bi-directional operation, and we could control that what kind of shift that we want. Either we want the data to move from right to left, or we would like to move data from left to right. Similarly, if we could add a functionality like a parallel road, in which we are able to parallelly add all the inputs into the registers or the flip-flops that are involved in the serial system, then we could also have n parallel output lines, so that we could get the data or the outputs in the form of parallel too. So it means that we could be getting the output value in the form of serial and in parallel, both of them. So in this way we could add an extra functionality to the system, and also we could add the same thing that we discussed in the parallel load thing, that if we want to retain the same value of the current register, then what kind of the functionality that we could add. So these are 7 different kinds of functionality that we could add to any register. So what we have done is we have designed a system in which our system performs all these kinds of functionalities. What we have done here is that we have a 4-bit system here, and this 4-bit system is originally designed in a way to perform say a serial input output operation. Say the data is entered from one side, and then data is retrieved from the output of the next signal here. So what we have done is we have added some extra circuitry here, so that our this system behaves in a way that we perform all those functionality that we have just defined in the last slide. What we do here is that we connect the input D of each of the flip-flop with the output of a 4x1 mux. So each input of this flip-flop is connected through a mux, and this mux is controlled by the 2 selection lines. So depending upon the values of these selection line S1 and S0, our system behaves in these 4 way. Say if both of the values S1 and S0 are equal to 0, then what would happen is that our system in that case would retain its values, and there would be no change in the output of A0, A1, A2 and A3. While if we have S0 equal to 1 and S1 equal to 0, then what would happen is that our system will move in a form of a shift register, but this time the shift would be the right shift. We would be moving from this direction, from left to right. If we select S1 equal to 0 and S0 equal to 0, then in that case our shift would be moving in this direction. So by appropriately selecting these control modes, we could move in either direction. We could move from here to here, or from A0 to A3. Similarly, if we have both of them equal to 1, S0 and S1 equal to 1, then what are we can do is we are able to connect all these external or the parallel inputs I1, not I1, I2 and I3 towards all the 4 flip-flops that are involved in this system. We were able to load all these values directly to this system. So in this way, what we have done here is that we have used a simple circuit of a serial transfer register, and we have manipulated the inputs of each of the flip-flops in a way that it could behave in various different kind of functionality depending upon that what kind of mode we have selected from this table. This would behave automatically. We would get, generally in a normal operation, we would be getting a serial input here at the D input, and we would be getting A3 as the output of the serial buffer. But we have also now put the output values here, so we could also get the parallel result here too. So if we would like to get the result in the parallel form, we would be just collecting the values from A0 to A3. So in this way we could get the result in a form of parallel. If we want to get the result in a form of a serial input and serial output, we could apply just here the different values here, and from these 4 input values
we could get the different results, because for each of these mode values, what we are doing here is that our system is connected to the certain input. Say for if we want to have a serial input from shift for the shift right, then what would be happening is that this mode would be getting selected from this condition. So if we have a direct or parallel load option, then what would happen? The last input value from each of these would be selected, and the values from I0 to I3 would be loaded to all these flip-flop. So in this way, we could add multiple functionalities to our normal shift register. Kindly do read these pages for better understanding.